Today we're going to be talking about mapping transformations, lesson 6.3. And our objective today is, given a point and a rigid transformation, I can write the coordinates of the image in 3 of 3 problems. So we've talked about what kinds of transformations are considered rigid. There were 3 of them we talked about. Do you remember what they are? They are translation, rotation, and reflection. And we're going to cover the 3 of those over 2 days. So we're just going to cover 2 of those today, and then we will do the following one tomorrow. So we're going to start out with translations. Now, in your own words, what is a translation? Pause the video, write down in your own words what you think a translation is. And now that you've come up with some ideas of what a translation is, maybe you wanted to describe something similar to this picture up here. Let's see what our official definition is. A translation is a transformation that moves every point of a figure by the same distance in a given direction. So remember when we were talking about translations, we had these vectors here, and they have a particular length and then a particular direction. And every single one of the points in our figure moved that same distance in the same direction. That's what a translation is. So you might have used words like shift or move. You might have mentioned that it stays the same size and shape, moved up and down, left or right. All of those are considered translations. Now we have a couple of ways of describing translations in problems. You might see them in words, like this first example here. Translate point A to -1, so there's 2, -1. Translate it 1 unit to the left and 3 units up. So we would go 1 to the left, 1, 2, 3 units up, and put a dot there. That would be A prime. Remember, prime is our image indicator. That indicates that A is our original object, A prime is our image after the transformation. Another way we can write problems is symbolically. We can say x, y, this coordinate pair x, y, goes to the rule x minus 1, y plus 3. This is the same as these words up here. X minus 1 is the same thing as 1 to the left, because x goes left and right, subtract is left, add is right. Y goes up and down, add is up, subtract is down. So this would be 1 unit left, 3 units up. So this is the exact same problem as up above. We would get that same image. Notice we can actually take these x and y values and put them in. So our x value is 2, and our y value is -1. So if we simplify those, we get 2 minus 1 is 1. -1 plus 3 is 2. And notice that is in fact the coordinate we got here, 1, 2. So you could do these a couple of different ways. You could either put them on a graph and count out the units, or you could just perform this arithmetic, and that will still work as well. So let's try a few of these. Translate point A, -7, 3, down 5 units and right 4 units. What are the coordinates of A prime? Go ahead and pause the video, give that one a try. Okay, so we're going to go down 5 and right 4. Down 1, 2, 3, 4, 5. Right 1, 2, 3, 4. That's our point right there. We go to -3, this one's -3, and then -2 down here. So our coordinate point is -3, -2. We would call that A prime. Let's try another one. So what should we do if there's no picture? They don't always give us a picture. This says translate point B, 0, 12, by the rule x, y goes to x minus 6, y minus 2. What are the coordinates of B prime? How might we figure this one out? Well, we can use our arithmetic, like we said before. We can put our x value in for x and our y value in for y. Remember, those came from our original point here. X is 0, y is 12. And then we just simplify those. 0 minus 6 is negative 6. 12 minus 2 is 10. But what if we like graphs? What if graphs are really appealing and we can really see what's happening with graphs? Well, we can actually draw our own graph, right? Nobody can stop us from drawing our own graph. So 0, 12, that means our x is 0, no left or right, and then we go up 12. 1, 2, 3, 4, 5. I'll put a big line every 5. 6, 7, 8, 9, 10, 11, 12. So that is where we start out. Maybe let's put a different color there. 0, 12. And we're going to go minus 6 on the xy. So we're going to go 6 to the left. And then minus 2 on the y. That's 2 down. So we're going to need to mark out 6 here. 1, 2, 3, 4, 5, 6. So we're going to go over to that 6, and then we're going to go down 1, 2. Put our new dot there. So this original one was b. This new one is b prime. And you can see this was 10, right? This was 5, 5, 10. We're now at the 10 on the y. And we went over to, this is negative 5, negative 6, negative 6 on the x. So our overall coordinates are negative 6, positive 10. Notice we got the same value whether we used a graph or whether we used the arithmetic. That's great. I love to see it when we verify our answer. Let's try another one. Translate the point C, 3, negative 5, by the rule xy goes to x plus 4, y minus 3. What are the coordinates of C prime? Pause the video. Try that one on your own. Okay, so we can put in our x and y value. 3 goes in for x. Negative 5 goes in for y. And we simplify. 3 plus 4 is 7. Negative 5 minus 3 is negative 8. And those are the coordinate values of C prime. Now once again, you're welcome to draw a graph if that helps you out, but I'm not going to draw it on this one. We'll just work with the arithmetic on this one. So that covers everything for translations. Now we're going to move on to rotations. So here's another example with a picture of a rotation. Pause the video and describe in your own words, write them down or type them out. What would you say is a rotation? How would you describe it? Okay, so now that you've written that down, maybe you use some words like spin, around. Maybe you mentioned there is a circle or even concentric circles. You might have mentioned there's a fixed center, or maybe something about the angle of rotation. Maybe you said something about the direction of rotation. All of these are great options for describing rotations. Let's see what our official definition says. A transformation that moves every point of a figure in the same direction, clockwise or counterclockwise, by the same angle around a fixed center. Now, notice this doesn't say anything about circles, but there are certain things in here that indicate circles, like a fixed center. That's what creates a circle. So when we have a fixed center with a length that we call a radius, r, and we spin that radius, we spin that point all the way around that fixed center, that creates a circle. That would be the same for all of these points. So we move every point in the figure around this same circle. We go the same angle measure, and we go the same direction. We either go counterclockwise or clockwise. Remember, a clock looks like this: 12, 1, 2, 3, 4, 5, 6, So this is clockwise, and this way is counterclockwise. So when we are in a physical school with physical paper, we'll typically do these with a compass and or a protractor. These are tools for measuring angles around a circle or drawing circles. But we don't have really great tools for these things quite yet online, so we're not going to be using any of the online tools. And instead we're going to be restricting the angles we look at to things that we can figure out intuitively rather than using tools. So we're going to limit what we're looking at to 90-degree rotations and multiples of 90 degrees. So that's 90, 180, 270, and then a full circle would be 360. That would end up where we began. We're going to limit our rotations to those. So when we rotate 90 degrees, remember we talked about quadrants. We talked about the quadrants in the coordinate plane, each being 90 degrees. Each of these is a right angle. And we said that was the case because if we drew a circle here, if we drew a circle with the center of the origin, we know that that has 360 degrees total, and we need to divide it by 4. So we know that each of these has 90 degrees each. That means that a 90-degree rotation is just moving one quadrant to the next, kind of rotating that quadrant up on its side. That would be the same if we were moving here to here or here to here. So this one asks us to rotate point A 90 degrees counterclockwise around the origin. And we can think of rotating this entire quadrant 90 degrees, so one quadrant. We're going to go counterclockwise, so this direction. And we're going to move this whole thing over here. That means our x-axis moves up to the y-axis. Our y-axis moves down to the x-axis. You can also look at it like turning your head to the side. Notice in this image picture, we actually did just rotate the numbers. So see how all the numbers are on the side, on their side, and the A is turned sideways. That's because we literally just rotated the picture. But if we renumber these now, how we're used to looking at them, this would be -1, -2, -3, -4, and this would be +1, 2, 3, and 4. We can find that our new point is -2, +3. This is A prime at -2, +3. And we did that just by rotating this entire quadrant. Another way to look at this, let me grab a highlighter. Another way to look at this is if we highlight this rectangle made by point A. You can see it's 3 units wide, 2 units tall. If you think of rotating that on its side, it's now going to be 3 units tall and 2 units wide, but it's still going to be connected at that origin because that's where we rotated around. Notice it said we rotated around the origin. So this R point stays the same. That stays solid, static, and we're just going to rotate this rectangle upwards. So we rotated up here, and 3 wide, 2 tall became 3 tall, 2 wide. You can imagine if we were to rotate it again, it would do the same thing, right? It would become 3 wide again, 2 tall, but down in this quadrant. So those are ways of thinking about rotations. Here's another example of a rotation. This one says to rotate point B 180 degrees clockwise. So keep an eye on those degree measures. Those tell us how many quadrants. 180 is going to be a 90 and then another 90. So we're going to go one quadrant clockwise and then another quadrant clockwise. So this will be the first rotation. Notice once again, we just literally rotated this picture on its side, but then we can renumber these. 1, 2, 3, 4, positive. These ones will be negative, 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 negative. And once again, we rotate to the second quadrant because this is a 90 plus a 90. So our first rotation and then our second rotation, we end up here. If we renumber these are positive 1, 2, 3, 4, and these are negative 1, negative 2, negative 3, negative 4. Our final location is 3, negative 1 for B prime. Now once again, we could think of this in terms of our little rectangles. So this is 3 long, 1 tall. Over here, it's going to be 3 tall, 1 long. So we flipped it on its side and moved the quadrant. And the third time, once again, we're going to flip it on its side and move the quadrant. So 3 long, 1 tall, 3 tall, 1 long, 3 long, 1 tall. And we end up here at 3, negative 1. Now, all of those examples we've looked at so far have the center of rotation as the origin. What if the center of rotation is not the origin? What should we do then? Well, you can imagine, just in your brain, think about moving the origin up to our new center of rotation. This one says we're going to rotate point C 90 degrees counterclockwise. Remember, clocks counterclockwise is this way. So we're down in this quadrant, we're going to move to that quadrant next. But we're going around point R, negative 2, 1. So instead of the origin, we're rotating around this point. So we can think of it actually the same way. The only difference is, instead of the origin being the static point, now this other point is going to be the static point, and we're going to envision the quadrants being over here. You can think of a dotted line here and a dotted line here, and we've sort of shifted the axes. But otherwise, it's exactly the same. We'll just take this whole quadrant and rotate it over here. I can draw my rectangle there. You can see it's 3 tall, 2 wide. We'll start at that same point, the center, and we're going to flip the rectangle on its side, 3 wide, 2 tall. We end up with this point C, which is 1, negative 1. All right, so we have a few for you to try on your own. Rotate point A, negative 1, 2, 90 degrees clockwise around point R, the origin. So you have a few things you need to ask yourself. Which direction? How many quadrants? Where does it end up? Pause the video, figure that out, come back, see if we get the same answer. All right, we are going clockwise, which means we're going from this quadrant to that one. If I draw in my rectangle here, we have 2 tall, 1 wide. That means when we rotate it, it's going to become 2 wide, 1 tall. It's going to be rotated onto its side, like that. Our new corner here is now 2, 1. That's the location of our image A prime. Let's try another one. Rotate point B to negative 3, 180 degrees clockwise around point R, the origin. So we need to ask ourselves, which direction? How many quadrants? What is the center? Pause the video, give that one a try, come back, see if we get the same answer. Okay, so here is my rectangle that I'm going to imagine rotating. And what direction are we going here? We're going 180 degrees clockwise. So this tells me I'm going 2 quadrants, right? A 90 and then a 90 again. And clockwise is this direction. This is the direction the clock goes. So there and then there. I'm going to end up in this quadrant. So if I draw my next rectangle, it's going to be flipped on its side again. And then one more time, flipped on its side, it'll be here. We end up with the corner being right here. So our image, B prime, is at -2, +3. So those are the coordinates of our image after a 180-degree clockwise rotation around the origin. All right, one more, and then we're done for the day. Rotate point C 4-1, right over here, 90 degrees counterclockwise around the point R, the origin. Give that one a try on your own, come back, see what answer we get. Okay, we're looking at 90 degrees counterclockwise, so this is counterclockwise. We're going to go to that quadrant. Here's our rectangle. If we rotate it 90 degrees this way, oops, we're going to end up with a tall rectangle now instead of a wide one. But it'll be the same dimensions, so we're going to have 4 up and then 1 across. So there's our new image rectangle. That's what happens when we rotate it 90 degrees this way. Our new corner is up here at -1, 4. And we call that C prime as the image of C. So that wraps up everything for our objective today. Given a point and a rigid transformation, I can write the coordinates of the image in 3 out of 3 problems. We covered translations and rotations today. We'll be covering reflections tomorrow.